Okay, so continue on this. Okay, so I've been using the term marginal distribution before. So if you remember the previous slide, okay, so I'm just gonna, let me, oops. Okay, yeah, this one, right? So remember I was saying that what we're getting here, they're the marginal distribution, okay, because it's about one variable at a time. Okay, not two or multiple at the same time. Okay, so now let's define what we mean by marginal distribution more carefully. Okay, I'm trying to use this example over here. Okay, alrighty. Okay, it's here. Okay, all right. So the marginal distribution, if I think about it, okay, say like now if I want to find out about the probability of b equals to 0, okay, what I need to do, I simply add them up. Okay, I'm adding all of this up because this is all of the joint probability, right? When b equals to 0 and w can be anything. Okay, so when I add this up, I will get this probability, and this will give me the probability of b equals to 0. Okay, and then notice I can do that for all of this ones, right? And all of this ones if I'm trying to get the probability of w in this case. So let me show you the values here. Okay, so this is when you add up like all of the each columns one by one, and then each rows one by one. Over here, you will see that, well, the marginal, or okay, the reason why we call it as marginal is because it's margin of the table. Okay, so this is the marginal distribution about b. Okay, that is looking at the probability of b equals to 0, 1, 2, and regardless of what w is. Okay, similarly, all of the ones down here, this is the marginal distributions or probabilities for w, regardless of what b takes. Okay, so this, if I try to like bring us back into the definition that we had earlier, okay, the definition when we talk about the joint CDF, if you remember, okay, let me try to get it. Yeah, okay. Yeah, even though here we're talking about the CDF, but if you remember what we're trying to talk just now is that, well, if you have the joint, right, in order to get the marginal, right, you pretty much just sort of like ignore the one that you're not working with, okay? And then that's, I would say, following the same logic as what we're doing over here, right? Like say up here, we're trying to get the marginal probability of b equals to 0, right? So we are essentially, let me just write it more mathematically over here, right? If I want to know probability of b equals to 0, okay, that is the same, right? As doing, I should, not the same, that's the sum of b equals to 0, right? W equals to 0, right? Plus, sorry about the notes here, okay? Plus b, a probability of b, oh, sorry, b and w, those are capital letters, okay? Equals to 0, and then w equals to 1, right? And then plus the third case, b equals to 0 and w equals to 2, okay? So that's why we're adding them up, okay? And this, if you remember, goes back to our law of total probability, okay? When you have, like now we're more formally defining it through joint distribution or joint probability to the marginal probability, but that's following the same logic as the law of total probability as well. Okay, alrighty, so formally, okay, and like I said, because the column and row sums of the distributions of b and w respectively, so what you can do, like I'm showing over here, for any like b, capital B takes any b value, right? That is the same as fixing the b as is, okay, but then you can allow any values of w to be happening, right? And you add them up, okay, and that will give you the marginal probability of capital B equals to b. Okay, similarly you do that for w. Okay, so these are the marginal distributions of b and w. Okay, and one thing I think an important takeaway for us is that if you have the joint, okay, you will be able to get the marginal for the two discrete random variable example down here. Okay. And in general, of course, if you want, and this is again goes back to the I think the law of total probability that I was talking about, right? Like generically, you have this, and then that is the same as summing up all of the joint probability by fixing x equals to x. Okay, but then of course, how do you get all of this, right? This is another important result that, well, if I have the joint, right, probability x equals to x and y equals to y, in the example that we saw, we kind of can compute it, right, with the socks example. But sometimes if you don't, then another way you can get it, right, is to get the marginal, okay, of y multiplies with the conditional of x given y. Okay, so now we are ready to introduce the conditional distribution concept. Okay, so this is a conditional distribution. Okay, we talked about conditional probability before. Okay, but now this is talking about conditional distribution. Okay, so formally, to define it, let me go to the next slide. Okay, so the conditional distribution, okay, is defined to be the ratio of the joint over the marginal. Okay, and here we're working with PMF. Okay, that's why we have this kind of notation. This notation wouldn't make sense at all for continuous because everywhere going to be 0. Okay, so that's why here specifically we're defining conditional distribution with for discrete random variables here. And I would say that in the live exercise session for the week, you will get some exercise of doing this conditional distribution calculation as well. Okay, but as you can see, probably wouldn't be too complicated to do, right? Because if you already have the joint, okay, like the table that we got, right? And then you compute the marginal by doing like adding the columns or adding the rows accordingly, then you should be able to get this conditional probability or conditional distribution, sorry, specifically for all of the different X and Y. Okay, so yeah, keep in mind we will get some exercises on that soon.